Okay, so we're going to begin today by talking about what the next 2 weeks are going to look like, sort of how just re-emphasizing the information from the email I sent out yesterday. Again, the school is, this is only a 2-week transition. Currently, we are planning to be back for regular classes in 2 weeks. So we'll be back for normal lecture on the 27th of October. For right now, for just these 2 weeks, we're going to have our lecture calls here via Google Meet. Even remotely, I still lose my train of thought way too often. I will be having class calls for all of the standard times, and since classroom size isn't an issue, I'm going to send the same code to the entire class regardless of whatever time that student is normally signed up for, because at least to me, it doesn't really matter which recording block someone tunes into right now, because it's all going to be the same material anyway. So the times that codes are going to go out, like the times that lectures or calls will be held, are all of the usual times for Physics 1000, which include Tuesday at 10 a.m., 12 p.m., and 1:30, Wednesday at 1:30, Thursday at 10 a.m., 12 p.m., and 1:30, and then Friday at 10 a.m. You can attend as many or as few of those calls as you want to. These calls are mostly going to be for me helping people with specific needs. I will still go through the lecture material, but I want to prioritize asking you guys what questions, concerns you guys have during these times, because I have already recorded the Chapter 5 and Chapter 6 lecture and sent out those links to those lectures for you guys to watch. Those were in the email from yesterday. And to sort of list the steps and procedures for this particular week, for these 2 weeks, I would say your first task in a week should be to watch those videos, because those videos are the lecture. As soon as you watch those, they go through the same slideshows, they go through all of the material, and you will have them and have access to them to watch and rewatch whenever you want to. You don't necessarily have to do it during this class time. And then you can come into these calls with any questions that you have. I am combining Chapter 5 and Chapter 6 together because they're both very short and they're both about pressure. So even though we're going to be covering 2 chapters this week, it's still going to be the same amount of content, the same amount of work as a normal week. We're combining 2 half chapters into a single week of study. So this week is going to be about Chapters 5 and 6, because they're really just 2 halves of a whole, 2 very short halves. And so your first objective this week should be to watch those videos for Chapter 5 and Chapter 6. Between them, there's only about 2 hours of lecture content, which is about what everyone. Normally, we have 3 hours of lecture content, so that's 2 of the 3 hours right there. And then you can come into any of these calls as often as you want to, and you can drop in and out with any of your questions. The purpose of these calls is not to force you all to be in them. If you, say, watch the tutorials, watch the video lectures, and feel you are fine with the material, if you don't have any questions, you do not necessarily need to be in here, in these calls. Because just because I'm having these calls very often doesn't mean you need to be sitting in front of your computer for any length of it if you don't need to. These times, like the Google Meet works best for, I find, helping everyone along. Because if I am just reciting the notes to you, I want there to be involvement during these calls. I want you to get something out of these calls that you couldn't just get from watching a video. So I recommend watching the videos so that when you tune into the calls, you can come in with questions and we can engage with each other and I can help you with your concerns. So first step for these 2 weeks is to watch the lectures I send you. You can do that whenever you want. It doesn't have to be during this time. You don't have to be in this call as you do it. They go through exactly the same notes, even though I recorded them over the summer or a summer section of Physics 1000. They cover exactly the same notes and exactly the same material. The important thing to be aware of is any comments at the beginning or end of a video about, say, scheduling and homework due dates. Those comments would be for a different class. So when you're watching those videos, do please disregard anything about due dates or scheduling. But all of the content, all of the lecture material is the same, is useful to you. Watch those, come to these calls, and I recommend you go ahead and begin working on the chapter 5, 6 combined. Again, 5 and 6 are going to be combined together. There's going to be one homework assignment, one quiz, and one lab for this week. All of those things are due next Tuesday. The lab is due next Tuesday along with the homework and quiz. The homework and quiz are now available to you. They are on, the homework and quiz are live on Sapling. The lab, I emailed the document out to you yesterday, but it's also available on Brightspace. So your order of operations for, sort of your step list for these 2 weeks are watch video tutorials, come to the calls with questions, do your work on your own time. You can come to these calls with questions about any part of the homework, quiz, or the lab. Specifically, I'll be in this call room. I'll be hosting calls during when our labs would normally meet. You don't have to be in that call to do your lab. You can work on your lab on your own time with anyone you want to. You don't have to be signed into a call to do so. The call is designed as sort of a drop in and out as you need it type of thing. If you do not actively need help, you don't have to be signed in, okay? I'm doing this to try to give you guys as much flexibility as possible because I'm aware things are weird right now. I want to give you guys as many options as possible if your schedules have changed based on what your current physical situation is. So, any questions so far about any of this information about the general procedure for these 2 weeks? And I'll give you guys a chance if you want to ask in the chat. Go ahead. If you have any questions, go ahead and make them known while I quickly take a sip of water. I find doing the video calls makes me thirstier because I'm doing more nonstop talking. Okay. If you have any questions at any time, please go ahead. You can turn on your mic and cut me off. I don't mind. You can put it in the chat. I will be reading it and watching it. Anything, anytime, please let me know. I'm going to screen share really quickly. So right now I am showing through Google Meet the screen on my computer. And I'm going to go to our Brightspace page to show you what I have added. So we have the content here on our Brightspace page. We have all of our chapter tabs to the left. There are now 2 new tabs, one for Chapter 5, Pressure and Buoyancy, and one for Chapter 6, Pressure in Fluid Systems. You click on the Chapter 5 tab, click on the tab itself, title, and a link to the video lecture. This is the same link that I sent you yesterday. It sends you to the YouTube video for the Chapter 5 lecture for Physics 1000. Again, please note, since this was recorded over the summer, disregard any due dates, scheduling, but again, same slideshow. In the video, I mentioned what slide you should be on as the video goes on. So it's the same slideshow, just I recommend having the notes up as you watch it, and also having the notes up during these calls too. In both the recording and in these calls, I'll have the notes up. I'll tell you what slide we're on, show you what you should be seeing. Click on the tab itself, and you have the link to this video. The Chapter 5 notes are located here. I did send out the slideshow yesterday. You also have a link to the lab assignment. So this is the lab. There's going to be one lab for Chapter 5 and 6 combined. Again, we're doing them both this week. We're just making one chapter out of these two short ones because they're both about pressure and how it affects things. So there's one lab this week that involves both Chapter 5 and 6. That one lab is here. It is pressure and buoyancy. Now, because this is a remote online lab, it's going to be using some simulators, and I do include in the lab document itself instructions for how to use those simulators and some screenshots of what you should be seeing as you work it. But to give you guys the tools to be able to work on this whenever you want, I have also included these two objects here beneath the lab itself. These are video tutorials that go through how to use the simulators in each part of the lab. So it's just a recording of me talking about the simulator itself and how to use it. There's two recordings here because the lab does involve two different simulations. Excuse me. The lab involves two different simulations, so these two tutorials are for the two different simulators. You refer to these at any time as you are working on your lab. You can also, again, ask me any questions you have while working your lab. You can work in groups. I do recommend you work in groups. You can do so remotely. If you are physically able and are comfortable working together, that is also fine. Working physically together, that is also fine. Just make good choices. And that's everything in the Chapter 5 tab. The Chapter 6 tab has the Chapter 6 notes. Again, where 5 and 6 are going to be joined together, and so there's one lab that is presently in the Chapter 5 section. All that information is here for you. I also sent out both slideshows and the lab in the, in the email I sent yesterday. Just emphasizing all this information. Pardon me. Sorry about that. So that can all be found here. And the homework is already live on Sapling. So just to go along, we have one homework assignment and one quiz for Chapter 5 and 6 combined. So these are both here. Everything is currently due October 20th, next Tuesday. That is 1 week from today. And just sort of the usual policy, everything will be due at midnight next Tuesday to give you time to come into our class calls on Tuesday and ask any questions you have as we finish things up. If I need to extend things past Tuesday, I absolutely will. But that is our current plan, our current due date for both the homework, the quiz, and the lab. The lab I will also take next Tuesday before midnight, because it's going to involve things that we're learning over the course of this week. So it's not due on your lab day. It is due next Tuesday. Now, stop presenting. As I said, I find these calls work best when people come with questions and we can discuss with each other the information that people need. So if anyone wants to, I feel like that is the basic information about how the course is going to work for these 2 weeks. We're going to resume to normal after these 2 weeks, but for these 2 weeks, this is the information about how it's going to work. And if any of you currently listening wish to simply check out of this call now and watch the tutorials or watch the videos, the video lectures, or and possibly drop back in and out as you have questions, you are welcome to do that. You do not have to stay here all of the time. These calls are for your convenience. They can be lecture, but they can also kind of be like office hours. So if you want to just say, stop here and watch those videos, you can. But I'm going to open the floor in a minute to questions. If there's nothing specific you guys want to talk about, I will just begin going over Chapter 5. We'll just start the material together, start going through everything, and just treat it like normal lecture from there. Let you guys decide what you want to be doing today. There's also, again, I'm going to send out another call at 1:30. That's when the lab time normally is. No one has to attend any times that they don't want to. Think of especially the lab times as office hours. It's times where I will be in this room in front of this camera answering any questions for anyone who shows up. You don't have to be working your lab in them. I know I'm repeating myself a lot, but I just tend to do that when I'm talking to the camera, I feel, because I don't have your expressions to gauge things off of. So, really quickly, does anyone have any comments, concerns, questions about these weeks, our general operating procedure, anything that you need? And if there's nothing specific, we'll just start talking about Chapter 5. Okay. Excuse me. So, all this material, I'm recording this so that you can go back and watch it whenever you need to. And we also have the pre-recorded ones if you want. So all of this material is available to you in many different forms. If we're gonna start talking about Chapter 5 now, and if you have any questions anytime, please cut me off. You can speak up on your mic. I'll also be checking the chat if you don't want to turn the microphone on. It's completely fine. And we're going to begin with Chapter 5. And I'm going to at least show you where you should be in the slideshow. Okay, so these are the Chapter 5 note slides, and I recommend when you are either watching the pre-recordings or going over material with me in here, that you have the notes open. If you have like a multiple monitor setup, you can put one on each setting. If not, you can be looking at the slide. So our Chapter 5 slides are about pressure acting on solids and fluids. So the main thing we're going to be talking about is pressure. To make sure that you have the right thing pulled up, this is the title slide. It is a nice shade of blue. All of the other slides in the presentation are white with blue at the top. So these are our Chapter 5 notes. And before we start talking about pressure itself, the physical concept of pressure as defined in physics, I want us to talk about the things that pressure is going to be acting on. And those things are solids and fluids. So move on to slide number 2. The slide is head titled States of Matter, and it shows various states of matter. So pressure always acts on something. Pressure is exerted upon something. Some things are usually made of matter. When you exert a force or put pressure on something, it is a physical object, and all physical objects are in some state of matter. And how they respond to pressure is going to depend somewhat on what state of matter the object is in, So let's talk a little bit about those states of matter. The three states that you should all be familiar with, the three that you have definitely most interacted with living on the surface of the Earth, are solid, liquid, and gas. These are listed in terms of rising temperature. Solids tends to be the coldest state of matter. Their particles are very tightly packed together. They form a rigid solid shape. And as you heat up solids, as you add thermal energy to a solid, eventually its particles will space out and melt into a liquid. If you keep hitting liquid, it will become a gas. All of these phases have distinct properties and behaviors separate from one another. And how they respond to pressure subsequently also depends on what state of matter it is. So, a solid object, we consider solids to have a definite volume and a definite shape. Solids have definite volume and a definite shape. That means if you take a solid object like my meter sword, this is a sword that I made out of a meter stick and a ruler. If you take this object, you can physically measure its dimensions, its x, y, and z axes, and you can figure out its volume. You can know how much three-dimensional space this particular object takes up. It also has a definite shape. This meter stick by itself will remain meter stick shaped until something comes in and forces the object to change. The only way to make this meter stick not the same shape is to physically break it, is to come in and forcibly change it by snapping it, setting it on fire, exerting some kind of a physical change. If nothing from the outside affects this object, it will always have the same volume and the same shape. So we consider solids to have a definite volume and a definite shape. Liquids, on the other hand, are a bit different. We consider a liquid to have a definite volume. Liquids have a definite volume. This is, so when you buy a gallon of water or a 2 liter of soda, gallons and liters are both measurements of volume. You can take that gallon of water and put it in another container, and it still takes up a gallon of space. But if I was to take my thermos of water and pour it into this Tupperware container, the shape of the water would change. Liquids do not have a definite shape on account of the fact that they are liquids. They flow. Their particles are not locked together. Liquids can change their shape. They still have a definite volume. 1 gallon of water, it will always be a gallon no matter what container you put it in. But liquids have a definite volume and not a definite shape. Now, heat up a liquid enough, it becomes a gas. Gases are unique in that they have neither a definite volume nor a definite shape. I hope that you guys are roughly familiar with, say, the helium tanks that you might get at a party store. So, like the tall cylindrical metal tank of helium has a valve on the side that you can turn, and you put a balloon on the nozzle and it inflates the balloon with helium. This tank has a definite volume and shape. It's made of metal. It's a physical object. The tank has a definite volume and shape. But notice, if you were to inflate a bunch of balloons from this one helium canister, so you just inflate a huge, absurd amount of party balloons from this one canister. The balloons have a different shape to the original tank, and the balloons occupy a greater volume than the tank by itself. One helium tank can inflate balloons that take up a much bigger volume than the tank itself. Because within this tank is a ton of helium gas that we had to use a machine to cram all of it in there, force it in there, force this huge amount of helium to occupy a volume smaller than it normally would. We were able to compress it using pressure. We compressed it with pressure in order to change its volume and its shape. Gases uniquely can do this. If you compress a liquid, it won't change its volume. But if you compress a gas, it will, or it can at least. So, those are the differences between the states of matter as they're going to relate to this particular section. And we're going to be studying the effects that pressure has on each of these things. Now, for that sake, I'm going to now divide these three states of matter into two categories. Now, solids are solids. They exhibit solid behaviors. Solids don't really act like liquids or gases. There's no commonality between solids and any of the other two. There's not many commonalities. Solids and liquids both have a definite volume, but because liquid doesn't have a definite shape, it can do something specific that solids can't. So liquids and gases, since they lack a definite shape, they can both flow. If you pour out a pitcher of water, the water is flowing. Wind is an example of air flowing. Liquids and gases can flow, but solids can't. Therefore, liquids and gases are both classified as types of fluid. Fluid can refer to either a liquid or a gas because they both exhibit fluid tendencies. They can both flow. Solids can't flow, so they are not fluids. So we are going to examine what happens when pressure is exerted on a solid versus what happens when pressure is exerted on different types of fluids. So when I say fluid in this chapter, it can refer to either liquid or gas. I know in English, a lot of people use the word to almost exclusively refer to water, but it can mean liquid or gas. And before we move past this particular slide, I do want to mention a couple of other things. The slide does mention that there are a couple different types of solids. There are crystalline solids, which form crystals. They have a very rigid and particular geometric structure. The other kind of solid is amorphous, which is everything that isn't a crystal. Those are just different types of solid objects. They're still solids. They all exhibit the same behavior. One additional thing to note is these are the three states of matter you have interacted with most in your lives because you are made of solids and liquids and you are constantly breathing a gas. But there are other states of matter. These are not the only three states of matter. If you change something's temperature enough, you can create a phase besides just these three. The most famous of which is called plasma. So you heat a solid, it becomes a liquid. You heat a liquid, it becomes a gas. When you heat a gas, you can get it hot enough to create a plasma. And plasma is important because it makes up stars, basically. Our sun is a giant ball of plasma. Plasma is essentially just superheated gas. You heat the gas up so much that it begins glowing and it begins exhibiting different electromagnetic tendencies, different enough to classify it as a separate state of matter. It behaves differently to a normal gas. And plasma is important because, again, our sun is made of plasma, which means we then therefore need plasma to be able to exist. Without plasma, we wouldn't have a sun, and we need our sun because it lights and warms the earth. And because stars are made of plasma, that means most of the matter in the universe that we know of and understand, most of the matter in the universe is actually in the plasma state. Because stars take up more mass and more volume than planets do, and stars are made of plasma. So most of the universe is actually plasma, but most of Earth specifically is solid, liquid, and gas. Now, there are places on planet Earth where you can find plasma. The two most common places are in light bulbs, because when you run electric current, the bulbs are all full of gas, and when you run current through the gas, it kind of flash turns into plasma and gives off light. Additionally, lightning does the same thing. When you see lightning, what's actually happening is the electric current turns the air it passes through into plasma, and it produces light, which is what creates the lightning flash. So, plasma exists, and it's important to know that it exists. But we're mostly going to focus on the first three. We've divided them into two categories. Plasma is technically a fluid, so it's worth noting that it exhibits fluid tendencies. We're going to talk mostly about the differences in behavior between solids and the fluids. So, that's what these chapters will be about pressure on these particular objects. As I'm clearing the board and setting up for the next part, if you guys have any questions really quickly, now's a good time to let me know. I'm also going to take a quick sip of water, so if you have anything at all, go ahead and let me know. All right. So, let's see. We're going to move on to the next slide. So, slide number 2 was the states of matter. Slide number 3, just to put a preview of it on the screen, we're going to talk about two new principles, two new variables, formulas, things we can measure. Those two things are, this marker's out of ink. We have density, and we have what these chapters are going to mainly be about. We're going to go ahead and define pressure. So, we're going to begin by talking about density. This is a concept that you should be familiar with. You have interacted with this before. Density is a measure of how much matter is contained within a particular amount of space. Now, physics ran out of good letters to use for our formulas a long time ago. And I apologize for that, because we used up the Latin alphabet, we used up the Greek alphabet, and so scientists just started repeating themselves after a while. This formula here is density equals mass divided by volume. This is a big capital letter V. This is for volume, not for velocity. This is not lowercase v for velocity. This is uppercase V for volume. Density equals mass divided by volume. This variable here is a lowercase rho, like with momentum. It is unfortunate that we use the same letter for both, but there's not going to be any momentum on the next test. Chapters 1 through 4 is over. The next test is going to be on chapters 5 through 8. So on your formula sheet, the formulas will be separated and labeled. So this is density equals mass over volume. Now, density, there was an internet video that was circulating a while ago. It was a clip of a gentleman from the UK talking about which was heavier, a kilogram of steel or a kilogram of feathers. And at the end of the video, someone set up a scale that had a 1 kilogram block of steel on one side, and then on the other side had a 1 kilogram pile of feathers. Now, kilograms is a measure of mass. 1 kilogram of steel, 1 kilogram of feathers. The mass on the same is both sides, so the force of gravity pulling on either side is the same. So these two objects, or two piles of objects, have the same mass. But steel is higher density, meaning that mass can be crammed into a smaller volume. The higher density something is, the more mass it has in a particular small space. Steel is higher density than feathers. It takes a lot of feathers. Each individual feather does not have a whole lot of mass. It takes a lot of feathers to create the same mass as this particular size block of steel. And because feathers have a lower density, that mass is going to take up a much bigger volume. So the density tells you how much mass is contained within a particular unit of volume. Now, mass is, as always, going to be measured in kilograms. Volume, there's actually a couple of different units that we usually use for volume. The standard metric unit for volume is liters, but meters cubed is also another valid measurement. Now, I want to go ahead and note, a liter and a meter cubed are not the same thing. 1 liter does not equal 1 meter cubed. They are different measurements of the same thing. They both measure some amount of 3D space, but they are not equal to one another. But because both of them are used, they're both metric, they're just different sizes. Because they're both used, acceptable units for density include kilograms per liter. They also include kilograms per meter cubed. These are both often used measures of density. Whichever one you have at any given moment just depends on the question you're looking at. And it's important to be aware of what units you have and are working with. So that's density. It's something you've worked with before. I'm sure you've had math and science problems about density. But now we're going to talk about pressure. This is our second definition, our second formula to help us get jump started on this chapter. So we're going to define pressure now. We're going to begin with the formula for pressure. And I'm trying to distinguish it in my handwriting. The variable for pressure is a large capital English P. This is different from the lowercase rho of density. It's also different from the lowercase rho of momentum. It is frustratingly the same one as power, isn't it? Dang it. Okay. But right now, for pressure, our variable is a capital English P. So this is pressure. Pressure is equal to force divided by surface area. This A stands for surface area. This is a big capital A. Now, to sort of explain this formula, you, as a person, have a surface area. You have a surface, you have a specific amount of surface. It's not easy to do so because we don't have a formula for surface area of a human, but you do have some specific amount of surface area, meters squared of material, that makes up your surface. And at all times, your entire body is surrounded by air. When you live at Earth's sea level in an atmosphere, there's a bunch of air around you all the time. And that air has mass. It's made of matter, so air has mass. That means that gravity from the Earth is pulling that air down on you all the time. So if I stick my hand out, there's air pressing down on the surface area of my forearm all the time. So that means the air is exerting a force on my surface area. And when you exert a force over a surface area, you are exerting a pressure over that surface area. Pressure tells you how much force is being exerted over a specific area. The more area you have, you're going to get more force from the same pressure. The more force you have on a specific area, the more pressure that you'll be exerting. Now, to compare this to your normal day-to-day life, I'm going to quickly draw a very poor representation of a human silhouette. So this is a very quick attempt at rendering the outline of an average human being. This person has a surface area. They have a 2D surface. And the air the force from the air is always going to point perpendicularly into the area of this person. Pressure pushes inwards on all sides of an object. So the air pressure on this person is always pressing into their body perpendicular to the orientation of the surface in question. If I stick my arm out, the air is going to push down on this part of my arm. If my arm is completely horizontal, that means the force from the pressure is going to be vertical. They are perpendicular to one another. But there's also air under my arm, and it's going to push up on my arm. The air all around you is always pressing into your body. You don't feel this necessarily because the human body was designed to live on Earth's surface. We're designed to work with and operate around Earth's air pressure. So we're accustomed to it. You don't notice it because your body is designed to tune it out. If you did notice it, it'd drive you crazy all the time. But you can feel something similar when you go underwater. Water is more dense than air. That means that there's going to be more water molecules pressing against your body. And so the farther deeper you dive down into some body of water, the water is going to exert more and more pressure on you. And humans do feel that. You can feel the increase in pressure from the water. And a lot of divers go through trouble because they have to deal with the water pressures that they are exposed to. Whenever you are surrounded by a fluid, there's going to be some pressure acting perpendicularly inwards on every single part of your body. This is by design. Our bodies are built to deal with this. So, pressure exerts a force over a surface area. You have a surface area, so the air pressure is exerting a force on you over that area. And it always points inwards. So on my side, the force is pointing inwards. On my front, the force is pointing inwards. On this side, it's pointing this way. On the top of my head, it points down. Sides of my head, it points in. It is always into the object it is acting on. So, the variable for pressure is a big capital P. The unit for pressure, the one we're going to be using mostly, is pascals. Pascals is abbreviated to just PA. This is the metric unit of pressure, pascals. There are also some other pressure units that you may have been exposed to. Scientists have invented a pressure unit called atmospheres. 1 atmosphere is the air pressure at room temperature on Earth's surface. So right now, I assume everyone listening is at sea level on Earth's surface, at least approximately. That means your body is presently under 1 atmosphere of air pressure. The unit was designed around what is the air pressure under Earth's atmosphere at Earth's surface. There's an older unit of pressure that I don't plan on using, but if you see it somewhere, I want you to know what it is. There's a very, very old unit called millimeters of mercury. So this is millimeters of mercury. The Latin, the chemical symbol for mercury is Hg on the periodic table. This unit came from the fact that all of our thermometers and barometers were based on air pressure and things like that. And you had to measure the pressure in the mercury that made up the thermometer. So this unit came from that old reason. This class, we are going to mainly be using pascals. You will occasionally need to convert back and forth from pascals to atmospheres. Excuse me. So that, I admit, has been quite a bit of information. I'll give you guys a chance to catch up, write things down, synthesize your notes while I take a sip of water. If you have any questions at all, now's a good time. Stay hydrated and stay healthy, everyone. It's very important. All right. If you move on to slide 4, we have a quick density sample question on slide 4. I'm going to clear the board quickly and try to do it in large print for you guys. I will keep the density formula up on the board, though. It's a quick density sample question. So on slide 4, we have we're talking about a boulder. And this boulder has a volume of 5 meters cubed. So this is the particular volume of this particular boulder. This boulder is made of granite, and granite is known to have a density of 2,691 kilograms per meter cubed. Every single material, any material you can think of, has a known density. So if you know what something is made of, you can usually look up its density. You'll always be given density in any problems where you need it. But oftentimes people can tell what something is based on its density. People have done a lot of experiments where if you don't know what something is, you throw it in water to measure its density, and you compare it to a table of known densities to figure out what that material is, since everything has a specific density. So we are told the volume and the density of this rock, and we want to know what its mass is. So mass is defined as, density is defined as mass divided by volume. So density equals m over v. We're going to start plugging things in. Our density is 2,691. We want m. Our volume was 5 meters cubed. Now we should check our units real quick just before we continue. Our density is given to us in kilograms per meter cubed, and our volume is meter cubed. So that means these units are going to cancel, and that's going to leave us with the kilograms that we want for mass. So we have our density is equal to our mass divided by our volume. So let's just solve for m. We're going to multiply both sides by 5. And that's going to give us a very large amount of kilograms because, scientifically speaking, boulders are heavy. But that shouldn't be news. And so the final mass of this particular boulder would be 13,455 kilograms. That is our boulder mass. Whoops. So, oftentimes, if you know the density of a material and the volume of a material, you can solve for its mass. It's very useful in terms of physics to be able to figure out what things are. Density is also useful because it helps us figure out if something is going to float. The old adage goes that if something is less dense than water, it will float in water, which is what we're going to start moving into. We're going to start talking about how you calculate that, how you know what that means, how you can predict that fact. So, give you guys a second. Any questions, any concerns before we move on? Any issues with this math? Anything at all? All right. I'm going to ask you guys go ahead and move on to slide 5 in the notes. I will begin sharing the screen so that you know which slide that is. So this is slide 5. The title is Facts About Pressure. Go ahead and peruse that. Look over it on your own copy as I clear the board to get ready for the next example. So pressure is defined as a force exerted over an area. This is the formula from a moment ago. And it increases with depth. Pressure increases with depth. So I'm going to paint a picture for you guys real quick. I'm going to draw another picture. Let's say that this line is the Earth's surface, which you are standing on. So this is you on Earth's surface. Now, Earth has an atmosphere. The atmosphere is all of the gases and the air, above us that surrounds the Earth. We can't breathe in space because there's no atmosphere in space, but Earth has an atmosphere. There's like a little, if you haven't pictured it before, if this is Earth, there's like a little cocoon of air around the planet that gets thinner the higher up you go. So we are in Earth's atmosphere. There's a particular height of atmosphere. There's a specific height of air above our heads at all times. So this line will represent the upper limits of Earth's atmosphere. This is the top of the atmosphere where it would end. There is an extreme amount of air between you and the top of the atmosphere. This height of air is huge. At all times, there is just a column of air above your heads going up to the upper atmosphere every moment of every day. And all of that air has weight. Earth's gravity is pulling down on that air. That's why Earth's atmosphere stays to the planet. Earth's gravity is pulling all of this air in like it pulls in everything else, because air is made of matter. Matter has mass, and there's a force of gravity between all objects with mass. That includes the air and the Earth itself. So all of the air above you has weight, and it's pushing down on you. That's where the force that creates the pressure comes from. So there's an extreme amount of force from the air pushing down on you right now. That force is exerted. All that air is just going to push into you. It's going to it's going to squeeze you, push into your body, because it's just trying to go somewhere. It's trying to escape, and it's pressing perpendicularly into every single part of your surface area. Now, when the slide says that pressure increases with depth, the deeper you are in a fluid, again, fluid can refer to liquid or gas, so the gas of our atmosphere is a fluid. The deeper you are in a fluid, the more pressure that fluid exerts on you. The more pressure the fluid will exert on you in that fluid. So say, for instance, we look not just at us standing on Earth's surface, let's also look at someone living on top of a mountain. If someone was living up here, there's not nearly as much air above their head. The higher up you go, the less air is above you, because the atmosphere is always right here. The height difference between you and the atmosphere is what determines how much air is above you. Up here, there's much less air pressing down on this person. That means that the pressure on that person is significantly lower. If we're talking about air pressure drops when you climb mountains or go flying. This is one reason why your ears tend to pop when you climb mountains. It's because there's a different amount of air pressure pressing into your ears, and your ears pop to adjust themselves to the new pressure. Same thing if you go diving very deep underwater. So the pressure that you're under from a given fluid depends on how deep you are within that fluid. And that gives us the formula on this particular slide. This is another formula for pressure. So, if you are submerged in a fluid, so I'll put a little caveat here. This formula applies when submerged a depth of h in a fluid with density rho. If you are in a fluid like we are right now, because we are in Earth's atmosphere, if you are in a fluid, that fluid is going to exert pressure on you, pressure equal to the density of the fluid. This is the density of the fluid around you. This is not your density. This is the fluid's density times 9.8 times the height of material above you. This represents your depth within the fluid. Like we were talking about with our two stick people over here. This person is far deeper down into the air than this person. So they're going to have a greater depth, a greater height of air above them, the H will be bigger. You plug in a larger H, and that person would have more pressure acting on them. So you can determine the amount of pressure acting upon you based on the fluid that you are surrounded in. Again, this is the density of the fluid. If we were trying to find the air pressure on our bodies, we would need to plug in the density of air, because that would be the fluid. Pressure equals density of the fluid you're submerged in times 9.8 times your depth within that fluid. And so these are our first two pressure formulas. These sort of form the backbone of the rest of the chapter. Now we're going to use these real quickly before the period ends. We're going to do one example that incorporates both of these pressure formulas, and then we'll call it for this lecture after that example. If you move on to slide number 6, I will present screen really quickly. So on slide 6, titled Pressure Sample, the problem reads, when you are 3 meters underwater, so it tells us that some person is at a height of 3 meters beneath the water's surface. It also tells us the density of water is 1,000 kilograms per meter cubed. We are asked for the pressure on that person. So to draw a picture of what's physically happening, let's say we have a pool. This is just a pool viewed from the side. There's a person in the pool, and that person is 3 meters beneath the water's surface. The first thing we're asked is, what is the pressure created, added to this person by that amount of water? So we know H, we know density, we want pressure. There's one formula that contains all of these, and that is this one. Pressure equals density times G times H. We're assuming this takes place on Earth, so we're going to assume that, as always, G is 9.8. That is the amount of gravity on Earth's surface. So pressure equals rho GH. Pressure is going to be equal to This is the density of the water. No, I need to rewrite this. This is the density of the water. So 1,000 times 9.8 times depth. So we have pressure equals 1,000 times 9.8 times 3. And that's going to give us some amount of pressure. That's going to be 29,400 pascals. And we're going to measure pressure in pascals. And that would be the pressure added to you by this amount of water. Now, in America, we don't really have, honestly, probably most people don't really have a sense of scale for what 1 pascal of pressure is. So to give you guys some context, the atmospheric air pressure that you are under right now is 101,325 pascals. 1 atmosphere's worth of air on Earth is over 100,000 pascals of pressure. You are under this pressure right now, and you are not even feeling it because your body is designed to work around it. So this amount of added pressure from the water is not something you'd notice. 3 meters below the water, you're not going to feel a tremendous amount of difference from that pressure being added to you. But this is how you find the number. And this number would increase the deeper you go. This is why, again, deep sea divers undergo a lot of very weird side effects from occasionally pressure sickness. The deeper you go into the water, the higher this added pressure gets. It's important to note that this pressure would be added to the air pressure that you're already under. This is just the pressure of the water on your body, not you would also still be under this amount of air pressure because there'd be a whole atmosphere's worth of air above this pool. That's worth noting.
Can you read it?
Sorry, I wasn't expecting you to speak. Can you say that again?
Can you read? Can you read what it says under the pGH when submerged depth at H? No, it's on the left. It's on the left side. Left side.
Oh, here?
Yeah.
Okay. All right. Sorry. If this is not very visible, I apologize.
No, it's just the quality of the screen.
Yeah, this is a qualification for when to use this formula. This formula is for when you are submerged in a fluid. So this pressure is created when you are some depth within a fluid, like in this pool here. So this person is 3 meters deep in the water. So this pressure comes from the density of the water times 9.8 times the depth in the pool. So this formula is to be used when you want the pressure created by a fluid that you are submerged in.
So the line is.
Sorry,
when
says when submerged a depth of H in a fluid with density rho.
In a fluid with density rho.
Yes. I realize my handwriting is bad normally and the screen quality doesn't help. Very good question. Thank you. And I'm sorry that it wasn't clear before. Yes. So this formula is for when you are submerged a depth of H in a fluid with density rho, which is what we did here to find the pressure added by this water. Now, the second thing we are asked on this example, this is the last thing we'll do today. If your eardrum has a surface area. So this is the surface area of your eardrum. Yeah. If your eardrum has an area of 4.85 times 10 to the negative fifth meters cubed, what is the force from the water pressing into your ears? So we know the pressure, we know the area of our eardrum, we want force. We're going to turn to our other formula for pressure, P equals F over A. Our pressure is 29,400. We want force. Our surface area is 7.85 times 10 to the negative fifth. Multiply area over to the other side. And you will find that if you are 3 meters beneath the water's surface, that water is exerting about 2.3 newtons on your eardrum. That's the force from the water on your eardrum, which in the grand scheme of things is not a lot, but I still don't want something pressing on my eardrum. It's a very sensitive part of your ear. However, the air pressure at the surface is already more than this force. So the air is already exerting more than this on your ear right now. Your ear is designed to be able to handle that force and that pressure and operate around it. But these are our first sample problems about our pressure formulas, and this is when the lecture period would normally end. So thank you for listening in today. I'm going to keep this channel open. In about 15 minutes, I'll resume here for the lab time. But again, you guys don't have to be in here if you are working on the lab. I don't think either of you have the Tuesday lab period anyway. If you guys want to be here, you are more than welcome. If you want to be here for the lab time.
I didn't mean to leave.
Sorry, say again, Grady.
I didn't mean to leave. Sorry, but what were you saying?
Oh, you're more than welcome to leave. I'm just saying that I will be here for lab if you or anyone else needs to tune in for help on anything, but you don't have to be. I'm just going to keep the channel open.
Did you get my online lab?
Which one? I have a tendency to leave emails unanswered and ungraded so that I know when to refer back to them.
Well, I know I did it. I'm just not. Honestly, forget if I send it to you or not. So if you didn't get it, then I can send it to you again. But I think we only did one online lab, so I have that completely done. I've had that done for a while. I just don't know because when I submitted my test, I saw like, oh, I still have this lab here. I don't know if I send it to him or not.
Yeah, I don't think I have your lab from last week.
Okay, I will definitely send that to you then.
Okay, thank you very much.
And then the lab this week, did you email that as well?
I did, and is also on Sapling. I can email you directly if you'd like me to.
I think I can find it if you send it.
Yeah, it should be attached to the email from yesterday, but I'll send it to you again if you want.
And then the Sapling thing, like I know you kept on extending it, but it didn't show up on my screen, so I just click on it and it wouldn't let me do anything for the chapter 4 at all.
For either of them or just one of them?
I mean, like the chapter 4 quiz, it would give the answer and it wouldn't let me like give it. But it says the time was increased, and then the chapter 4 quiz or the chapter 4 homework, it just said that the due date's been passed and then wouldn't give me access to anything.
Hmm. That is very bizarre. And it sounds like you've been the only one reporting this issue, so I don't want to discount your struggles. It just means I have no idea what's going on.
I can try it again right now.
Well, I need to access your copies of it real quick. I am going to tinker with that, and I will email you if I find anything. So I will let you know quickly. I'm just going to stop the recording so that this is concise to just a lecture. I'll be back on this channel in a second. Grady, I'll let you know if I find anything shortly.
All right. Thank you.
All right. Thank you, guys. And if I don't talk to you again today, have a wonderful day.